So, hello everyone. So what we're gonna do, I have a quick announcement. So there's an NCAA baseball happening this weekend, starting on Friday here in Athens. So please go ahead and make your transportation back. Try to go ahead and reserve your shuttle reservation or make arrangements if you're carpooling together. Okay, so with that said, our next speaker is Paul Balmer, and he will be talking about Tate intermediate value theory.
Thank you. Can you hear me fine? Yes. We start by wishing them a happy birthday. I don't have last slide because I'm writing. And we start also by thanking the organizers for having me speak today and for setting up things so nicely that basically all the notation I'm going to use have been introduced in Manuel's talk or in Tensor. So it's fantastic. Just adding an assumption, everything is commutative in the sense that my tensor is symmetric modulated. So I don't know if these things will have an incarnation outside of this world. Okay, so this is joint work which is in progress with Beren Sanders at UCC. And I will try to point out that a few places where it is in progress, where we could do better. So I have to write at the same time as talk, and I've done that, I think, only once in the past in a conference, and it was a disaster. So I think the bar is low, hopefully do better. So the story is about, we're studying a tensor triangulated category K. So it's some TT geometry, tensor triangular geometry, and we want to study the spectrum of this tensor triangulated category, which you should think of, you could think in different ways. One is, well, maybe you think of it as a kind of a universal space on which you can describe the support of objects. So every object in K will have a closed piece in that spectrum that behaves nicely with A, with direct sum, tensor, and triangles, and it's the universal definition of the spectrum. That's the definition of the spectrum. It happens to be made of prime ideals, and the topology is almost the Zariski topology. It's a reversal, but the guiding principle is that it's the universal support data. And but you could also think of it a bit like you think of the spectrum of commutative rings, where you have primes included in one another, and so I will typically be using sometimes notation like that, where I'm talking about points and lines like that. So just to be clear, when I draw a line like that, with the P and the Q, it means that P is a specialization of Q. So P is in the closure of Q, or Q, I don't know.
Do you want to take questions?
I want to take questions, yes.
What is spec K? Is it a local space?
Spec K is the spectrum of this tensor triangle. Just a topological space, just a space. But very much as a space, but not just a set, because that's the point of the talk. So the point of the talk is that, so how do you compute this gadget in practice? When you go around and try to compute it. Well, there are the historical examples where people had done the classification of tensor, big tensor, something TT ideals. And then the spectrum will be the space that they used for the classification if they did their work nicely. But in the newer examples where we don't know the space, we compute it and we use the classification as a corollary. Knowing the classification of TT ideal or knowing the space is the same information as was explained in both of the previous talks. So in those cases, you compute it piece by piece. So you compute it piece by piece. And what I mean by that is that typically what happens is I have in mind examples like the equivalent stable homotopy category in topology. So in homotopy theory, the equivalent version of the chromatic homotopy, the chromatic power, the chromatic filtration, was done also with Beren a few years ago. And the key idea was that there are, for every group, there are two pieces you can do on the the category that depends on the group. One is the geometric fixed point, which is the same thing as killing everything that comes from proper subgroups in a very sense, localizing sense. And that will give you an open piece of the spectrum. And you can use restriction to proper subgroups to detect the rest. And you can say, well, for proper subgroups, by induction on the order of the group, I probably already know the answer, and so I will know this closed piece. So what happens very often, and that's, that has happened again and again, and it's just because of functoriality. So if you have a TT functor from K to a guy you know better, then you have an induced map backwards. Just take the, if you like to write it in terms of primes, it's just taking the primage of the prime by n. And so if you know the classification for L, you will get a piece of the classification for K, namely the image of this map. So what happens very often is that you kind of know that you know the spectrum as a set, and you know it is made of a closed piece that you know well, that is as a topological space, you know why completely, and an open piece. And this disjoint union is not as spaces, but just as sets. Okay. Let me draw obvious picture. So if I revert to this way of drawing the spectrum, and you think, okay, I have this closed piece Y, and I have an open piece U. And okay, bear with me a moment. I'm going to play a little bit with this. I want to move the chips. Maybe I didn't make it too big. So that stuff here. And suppose I'm keeping here only that's why people invented slides, is that you don't have to see me do that in public. But let's try. Okay, so you have the two pieces. And you ask yourself, okay, I know pretty well both of them. What is this? I'm sorry. That is not what to do. And I don't know why my selection tool has disappeared. Okay. So you know the two pieces, and you're asking yourself, well, how do those pieces fit together? I know that the space will be made of those two pieces, but maybe maybe it's like that, maybe it's here, maybe they're just disjoint. How do I decide that the two pieces fit exactly like that? What information can I hook up to decide how to patch the two pieces? The one thing you know is that it is not going to be like that, where if you write specialization upwards. So if you write specialization first, there won't be no intersection because they are disjoint. But it won't be like that, because this would give you an example of, you would have here 2 points where this point here has something in its closure that is in U, but Y is closed, so there's nothing in its closure that gets outside of U. Okay, so this is not going to happen. You have some restrictions like that. But it's a bit difficult to decide just by knowing the two spaces what the union as a space is. And really what could very well happen is exactly what Kent explained in his talk, that you can have just a disjoint union, which means that the category could split in two pieces. So if the spectrum of K was just the disjoint union as spaces, then K would split as two things, K supported on Y. And these two would be themselves perfectly acceptable T categories, and the K would just be the sum of the two. So that's kind of example 0. It's really what we don't care about. We don't want to have just the disjoint union of the two spaces as spaces. We don't want U to be also closed and Y to be also open. Okay, so what is the Well, we could of course take maybe an example one, which is a toy example, the smallest of all. If I take, except for taking either y or u empty, what if y was a single point and u was a single point? But there are really two options. Either we are in this disjoint setting that I just discussed, or y is the specialization of the point in u. And this, of course, happens. It's the spectrum that you would get if you take the derived category of discrete valuation ring, you would get that thing. And this can, of course, and one has to decide, well, if I just know that the space has 2 points, how do I know that it's disconnected or connected? Well, this will be, you have many arguments for just 2 points. You can say, okay, this one, for instance, is local. It would force the endomorphism of the unit to be local. So that you can just compute the endomorphism of the unit, pi 0 of your category. And if it's not, if it's not disconnected, in that case, the endomorphism will be disconnected. Would be the product of 2 rings. And so that's very easy to detect. Okay? So you don't need a sophisticated theory to discuss those two. But the more and more complicated the y's and the u get, the harder and harder the question. Okay. So what the main question is, what is the glue? What is the thing that comes in the middle? Let me maybe use another color. What is the thing that comes here in this picture that makes us know how they matched? And that's what I want to explain again in this general theoretic geometry. Is there any question about what is happening? So at that stage, I was a bit worried because I thought maybe I will have to lose the audience with introducing the definition of the Tate ring. But luckily, Kent, and it was not prepared, I promise this will not set up, explain to you the localization and the completion idempotence essentially. So let me remind you of something you learned half an hour ago, maybe an hour ago, some of you, or that you might have learned earlier. About localization. So I think I have y this piece of the spectrum of K. Out of that, and I'm assuming here, as exactly as in Kent's talk, that we assume that K is actually, and it's a very small assumption if you're ready to use borders and stuff like that. You can always, how did you call it? Indice, incomplete, so complete for direct sum or co-limits your category. So I'm assuming that K is the compact objects or the dualizable objects, namely the small objects in a big TT category. So, namely, it has to be compactly generated. It's generated by those compacts. And usually the story of compactly generated category has nothing to do with the tensor. Just, you know, you have the compact objects are the small guys, and they generate the whole thing and try to control the whole story from the small guy. But when you have a tensor, you have two notions of smallness. You have the compact story, which is kind of a story, or you can say, well, what about being dualizable? So a vector space being dualizable is being finite dimensional. So you can think, you know, dualizable is also a notion of smallness, and we assume that the two coincide. And it's a very common setup in commutative TT geometry. The derived category scheme will be like that. The stable category of KG module for a finite group scheme would be like that. The stable homotopy category in topology is like that. The G equivalent story for compactly group is like that, and on and on. Okay, so there are lots of examples of this set. It's a very small assumption to require that. And in fact, if you didn't have the big T, you would just use the dualizable, which is the whole of K, and use incomplete address. Okay, so from the classification, when I have a piece of the spectrum, I can produce a TT ideal, which I will denote KY, and we have seen that already today, is the objects in K whose support happens to be in Y. And if you think geometrically, okay, this closed piece and this open piece, that closed piece and open piece, if I want to go to the open piece, probably everything which is supported on that closed piece should go to 0. If you want to restrict from a geometric setting to an open piece, everything which is supported on the closed complement should disappear. And that's exactly what we do. We take the localizing category generated by this thing, and my notation will be T supported on Y. That sits as a subcategory, let me write inclusion like that. The only difference we can talk is that my functors are vertical, because then I don't have to tell you which one is left and right adjoint. You can just look at it. So you can put T inside, Ty inside T, and you can do the quotient, the Verdier quotient, T modulo Ty. It's a Bausch field localization, it's a finite localization, it's a smashing localization, has lots of names in topology and around. And one of the results of Neyman in this setting is that you can actually identify this with just the right orthogonal of this. And that's also something that Kent mentioned. So you can take the right orthogonal of this category. And it has the advantage that if you kind of think more as the right orthogonal as being the right object and the other thing as being the accidental interpretation, then you really think of this orthogonal as sitting inside the big category. So I should put here an inclusion, and then someone has to work to produce this adjoint instead of just saying it's a Verdier quotient. Well, you have to produce this left adjoint with this inclusion. I'm going to talk about how you produce it. But this category morally is exactly what you should think of as the category over U. So I'm going to write with a restriction to U, or sometimes in the past I've used the notation T of U or something. Let me just write T restricted to. And again, maybe that's a slight correction to what I answered to Eric. I'm thinking of the spectrum together with this free sheaf of categories. For every open, I have a category restricted to the open. It's in the background for free. So you have this right adjoint. You also have a right adjoint here. That was in Kent's talk. And every sequence that you see is an exact sequence. You can, if you take, if you take this as the kernel, as a subcategory in here, and you do the quotient, you will actually get this. And then if you use what I just said, well, if you can identify a quotient as the orthogonal of what you are killing, as long as the category is localizing, and this is still the case for this, for the bottom one, then you can also identify the top one as will become equivalent. Oops, that's horrible. From 10. This will become equivalent to Ty, orthogonal. Orthogonal, with two layers of orthogonal. But in particular, you have one more layer of adjoints here, and one more. Now, I probably owe you to a way of constructing those adjoints. And the very nice thing about the so-called Bausch field idempotent, or the Rickert idempotence, is that something that in this generality I did with Jordan Favi, is that once you know what happens to the unit of your category, what do I mean by know what happens? You say, okay, well, I have the unit of the category, the unit for the tensor product. Okay? By the general nonsense I explained here, there will be a left idempotent and a right idempotent. There will be an exact triangle, this is an exact triangle in T, which has the property that this gadget here lives in Ty, so it is in the localizing category generated by the compact object supported on Y. It is actually a sequential colimit of objects supported on Y. That's a little better. And this guy is just its code. So if you have an actual example, you can compute this in actual examples. Use a closing complex or stuff like that to do those actual computations. And this is in the localizing category. And then once you have done that for the unit, so you have in other words, this is, if I think in Kent's notation, this would be I lower star, I upper star of 1, 1, you use J lower star, J upper star. Well, there was a shriek here, a shriek of 1. So Kent told us about that for any object A. And what I'm telling you is that once you know it for the units, you know everything. The answer for A will just tensor this one with A. And in the middle, you will get one tensor A, which is A. On the left, you will get what you need, the ILO star values. On the right, you get all these adjoints here, which look a bit mysterious. They're all known once you know those two idempotents. And basically, once you know one, because the other one is the form, the map. So, for instance, here this will be EY tensor. This will be FY tensor. This will be the inner Hom from EY into blank. This will be the inner Hom. So there is an internal Hom in these categories that's also a consequence of round opposability, or you can assume that you have it in the first place. So that's the internal Hom in the category. And FY. That's how all these adjoints, they are known once you know these two elements. So one of the things you can do is, there are in particular two interesting gadgets. There is the completion, and the completion is the completion of Y is just this other function here. Actually, you can pre-compose with that if you want. It doesn't hurt. The EY will disappear because of terminality. Let's write it in the simplest form. It's EY. Okay, let me walk back a little bit just to make sure that you are comfortable with those three categories, or reasonably comfortable with those three categories. So we started with this big tensor triangulated category. We have a closed piece of the spectrum. We call U its complement. Okay, so U is the complement of. Should I clarify that? It's as in the setup above, right? U is the complement. Why? And we can produce morally what is the category over U. We know what T of U is explicitly. And if we think that we should recover the spectrum from U and Y, well, perhaps this thing here should be something like the category over Y. And it is a little bit, but not quite. So let me talk a bit about that. First, the nice part, the T over U. So this thing here is really T over U. Let me put the comments maybe in color here. So this is T restricted to U. And you might ask, well, if I come in algebraic geometry and T was the derived category of the scheme, and I do this game, well, yes, you will get the derived category of the open scheme. That's a legitimate thing to do. And its unit here, the unit of T restricted to U, many indices here, well, it's just this gadget F. I mentioned it's F1. So, and you should think maybe R goes to a localization R1 over S, right? That's really what this map is. So the Fy is just the unit in this category, and this is a perfectly fine big TT category. This is also still a big TT category. And just to finish convincing you that it's the right gadget, if I compute its spectrum of this T restricted to U, so including those of you who never heard of the spectrum before today, I hope you have a guess what this is. U, brilliant. Yes, T restricted to U, so the spectrum should just be U, right? You started with T. Okay. So, of course, you take the compact. Now, let's turn to the other one. Let's turn to Ty and ask ourselves, well, is that one, and let me use a slightly more ominous color. This guy here is a compactly generated category. After all, we generated it from compact, so it is a compactly generated category. Thank you very much. And it has a tensor product. It's a tensor ideal. And its unit will be EY. So this is a TT category. Please don't paste an image now. This is a TT category. It's not quite what I call a big TT category. It's a large TT category. It's a TT category. It's a compactly generated TT category. Its unit for the tensor will just be, guess what? EY. This is really just a triangle between the units of the three categories that we are playing with. But the problem is that this unit is very not compact. It is a large object. Typically not compact. Actually, it will be compact if and only if you are in the split setting at Kenton. So if Y is just also open, and then it will. So it's kind of never compact when we care about it, rarely. And so it means that this category, in that category, you have to distinguish the two notions of smallness. You can say compact, or you can say rigid, dualizable, like you think finite dimensional for tensor vector spaces. And well, if you want the unit to be in your category, you better go for the dualizable. The rigid, they fall aside, right? Because the unit won't be compact. Okay? So you have to use the rigid. So the correct category here, the correct, morally correct small category is you take Ty and you take the dualized. Now, in the background, there's another motivation. There's a posterior motivation, which is recent theorem, I think this year, and it's going to appear in the coming months. I don't think it has been published yet, of DIK, Benson, Iyengar, Krause, and Bevtsova, DIKP, that if you start with the derived category of a Noetherian ring, and you take Y for subsets, and you do this construction, and you look at the dualizable, you will get something that is equivalent to the perfect complexes over the completion type. And so that thingy here is actually morally the completion of your TT category at one. So the notation for that probably work in progress. So it might change in the future, but I'm going to call that the completion of K along one. And that is a respectable rigid TT category, a small TT category. And if you needed the large one in which it sits, it won't be Ty morally. It would be its incompletion, which would be something different. It would be a world in which those guys become compact. It will contain the other compacts, but it will have more compacts. Okay? So just be careful. The Ty at the top here is probably not, I'm not saying that big Ty in the ring case is the derived category of the completion. That is not true. It is the derived category of the completion supported on Y. So same story in Y. In the ring and in the completion, if you just take the parts supported on Y, they give the same answer. But in the complete case, there is this miracle that the perfect complexes, they can be seen completely from their parts supported on Y, which is a bit strange, but it's from via the right adjoint, not via the inclusion of the guys with support on Y. That would be obviously wrong. Okay, are you still somewhat with me? Yes. So the notation, that's completion, and you can think of completion as going now from our category we started from. You can think of as the compact in T, the compact and the rigid and the dualizable in T, and it goes to Ky, K completed along Y, and just be a little careful that it is defined as the dualizable in Ty. I'm just repeating what I wrote on the previous slide or the previous screen, but I'm not saying that this is what deserves the name T completed along Y. This thing will be the incompletion of that when that exists. Okay? And that, if you are an infinity category person, you say, well, it exists. I can just incomplete this thing. What are you doing? But of taste. So it's not a big deal to have the big category containing Ky, but I'm not going along that line now. Okay, now maybe a first result, first little theorem. If you look at what happens in the spectrum, so you have a map from spec K completed along Y, around just the extension, okay, the map induced by completion. Well, there is in here, let's call it phi maybe. So you have Y here, and you have the preimage of Y. Well, along that piece, it's a bijection. So if you're thinking, oh, I'm not completing rings along crazy things, I'm just completing local rings at the maximal ideal. So you're completing at one point, and this is saying, okay, the completion is still a local ring. It's only one close point about that. It won't be something crazy, but you don't, the rest is really difficult in general. And so for those of you who have done a little completion of rings, it can be a bit nasty. I'll give you an example in a moment. So along y, it's a bijection, and on the complement of y, our friend u here, well, we have phi inverse of u, and kind of there will be, that's nothing, I'm just describing the complement. And there is some interest in doing that, in understanding what happens on the complement of u, and that's where the Tate object comes in. So there is this notion, and that goes back to Greenlee's, I mean, in that setup, that brought in Tate homology before that. So let me give credit to Greenlee's. And it's a definition, so I don't know if it's credit in the definition. Nice definition. The Tate ring along y, dy, is, well, you do two things. So, well, technically it is this. It's fy tensor dy 1, and then you might be, oh my God, what is this? If you've never seen it before, you might be a bit terrified. But just if we use a little bit of notation, you take the unit, you complete it along y, that creates an object, which, by what I just said, along y is what you expect. There's nothing new happening on y itself when you complete along y. But there is stuff happening on the fringe of y. So you restrict away from y. So you just restrict. Remind you that tensoring with fy is just restricting to the complement. So you restrict to the complement of y. You complete along y, and then you restrict to the complement. That's what the Tate ring is. You can do a Tate construction for any object. You put here the object here instead of one. You can take the Tate of whatever. And the Tate of whatever is a module of the Tate ring. It's because whatever is a module of a one and lacks monodality and things. So that's a nice little ring that shows up whenever you have a y, you have this. Well, I don't know what I'm doing. Nice little. There is a nice little isomorphism you can prove about this boxes. Yes. This is always, Greenlee's calls it the Warwick isomorphism, I think, because he was not at Warwick at the time. I don't know if he wanted to draw the Warwick. He now is at Warwick. But he calls it the Warwick isomorphism. I think he proved it on his way to Warwick on visit or something like that. I don't know. I forgot the history. This thing is also the inner Hom from Fy to sigma of Ey. And you might say, well, who cares? That looks like another technical thing. Yeah, well, you should care a little bit because, for instance, the pi naught of that thing is just a homomorphism from this guy to this guy. That's what the internal Hom does for you. Or if you don't distinguish internal Homs and Homs anyway, I'm just talking about the homomorphism from Fy to the suspension of Ty. And if we go back to this little triangle, I didn't finish my triangle here, but here is the suspension of Ey. And you should get a feeling that, well, there is probably some interesting information in this morphism, right? For instance, if this morphism was 0, this would, again, as a sanity check, this would split. And this would, again, be the case where there is actually no connection between the two pieces, Y and the U. It would just be two different disjoints. And so this internal Hom here, which happens to be the Tate ring, plays an important role. Okay. Is anyone concerned about why this is a ring? It's just formal business. Look, the E is a co-ring, the F is a ring. So when you dualize the E and the tensor with F, you're good. Okay. So what is this Tate intermediate value theorem? We were very happy about it when we proved it, and then I will temper a bit the enthusiasm in a moment. The Tate intermediate value. We first proved it, and then we found a funny name. So what does it say? Well, it says, let's go back to our picture. Y, in fact, in my picture there. Y, and I told you, well, let me try to draw the support of the Tate ring. Oh, this morning I read the abstract I had sent a couple of weeks ago, and it says something about talking about the support of big objects. I promised a review of that. That will turn out to be a lie. I won't have time to do that. So, but I'm going to use the support of a big object now. This Tate ring is not a compact object; it's a big object, and I'm using the support of this Tate ring. And the support of the Tate ring lives here. It lives at the fringe outside of Y in U, right? So you should hopefully have understood that from what I said. So you complete. If you complete, you would get stuff that lives all over the place. But then you remove what is supported on Y, and so you just have stuff outside on the U part. U is this. So here is my support of the Tate ring. So there's a notion of support of arbitrarily big objects in the spectrum, or technically in the homological spectrum, that you can project down. And it's a nice theory which works quite nicely, and I think it has not been completely absorbed by the TT community yet, so I wanted to advertise it also too. With no assumption whatsoever on categories, homogeneity, nothing. Just you always have that, and it works very nicely for rings, for instance. It has a tensor formula. And so what the theorem is saying is, if you take a point in here, so what we care about is understanding who specializes to, who in U specializes to who in Y. So if you have a P1 in Y, a point in Y, another point in U, and we want to know when is P1 in the closure of P2. Maybe I use a P, what is P? We go P0. So I want to know in the algebraic geometry notation, sometimes we write like that to specialize it. So it just says P1 is in the closure of P0. So this happens if and only if, well, there exists an intermediate value. So there exists a Q, which is in the support of the Tate ring. So it refines this idea that if the Tate ring was 0, the category would split. Well, okay, but what if the Tate ring is not 0? Well, its support will actually tell you how to attach points in the open and in the closed, which is an intermediate value that P0 specializes to Q and Q specializes. So there must be, if you want this guy to specialize to this one, there must be a Q in between in the support of the Tate ring, such that the specialization passes by this intermediate value. Okay. Now you notice that this part here of the story, that is completely in U. So if you start by boasting, oh, I know my topological space U completely, well, how completely? Well, you should be able to decide that. And then the question is, when do you understand that completely? Because that's still going across the border, right? And the nice thing is you can refine this theorem a little bit. In fact, you can find Q will be the image of a Q prime. The Q prime is now in the spectrum of the compression. So now if you want, what I'm after is really almost this thing here. I'm talking almost about that. It's not quite that. It's a space that lives above that. And it's the space I was talking about here. This space here. I told you over Y it's a bijection, but there is some stuff over it. And what it will reach is exactly the support of the Tate ring. So this will suggest, it will suggest the support of the Tate ring. Beautiful. And so, as I said, more precisely, what is happening is that the Q is the image of the Q prime, and the Q prime specializes to, I'm going to abuse notation here and say P1. Technically, the P1 would be in the spectrum of the completion, but I told you over Y, it's a bijection. So you can think of P1 as living in the completion or down, it doesn't matter. So the second bubble here is also something understood, at least if you know this space. I told you, you cannot hope to know the answer just from knowing Y and U. You cannot, because it could just be the disjoint union. We don't know how they come. You need an additional information. And the additional information is the completion. We need to have a handle on this compression. And another way of formulating that, the variant, that if you go back to the picture I was drawing here, I'm going to try to save time by doing this, and probably I'm going to waste it. That, well, I could have cut the U as well. So Q here, and I have here pi inverse of U. So this is a pullback by definition. Okay? I'm just taking the preimage of U along this map file. And what I'm saying is that this is actually a push out. Is a push out in the category of topological spaces. Now, ideally, I would like to say that in the category of spectral spaces for the specialists in the audience, which has a stronger meaning in terms of the classification, but as a topological space, the spectrum of K is the spectrum of the completion, the open complement, and they get attached along essentially the preimage of the Tate ring that's in the completion. Support of the Tate ring, but seen as an object in the completion, not seen in the category. So we were very happy, and at some point we started worrying a bit. Yeah, what about this this thing here? Could it be actually everything? It's everything. It's kind of a bit lame, right? And in commutative algebra, if your ring is Noetherian and you're computing a, say, local Noetherian, you're computing a close point, you have some assumption about y containing the close point, something like that, then it will be everything, because essentially because a local ring injects in its completion the Noetherian case. So the intersection of the maximal ideals, in the intersection of the powers of the maximal ideal is Nakayama, 13 rees probably. The intersection of the power of the maximal ideal, that's 0. It's Nakayama. It's an ideal which is finitely limited and which has the property that it is m times itself. M is the maximal. So it has to be 0. And actually, you can build little examples where this even in commutative algebra, it's not true in general. Theorem. So you can find, and it's very close to my baby example. I started with this, 2 points. Sorry. So what about 3 points? So can we do an interesting example where y would be a single point and u would be 2 points? Well, what can happen then? Well, we have 3 options. We have the disjoint story, always there. We have maybe only the bottom point specializes to, so I'm maybe depicting U. Let me circle the U part. This is U. So of course here. But let's pretend that U could be just those 2 points. Or it could be something like that. The top point in U does specialize to Y, and this, if you just do meditation, there's no other option. And so, for instance, okay, I told you this. Whatever the categories are in the first place, you can just take the Cartesian product of the two. It's very easy to produce an example like that. Derived category ring cross the derived category VR. This actually does happen. This spectrum does appear. If you take, in representation theory, actually, if you take the homotopy category, the bounded complexes of, well, let me give you the simplest case, but so you take a field of characteristic 2, and you take the cyclic group of order 2, and you take KC2 modules, and you take bounded complex up to homotopy and the usual tensor. The spectrum has this shape, has three points. And the circle part would be the derived category. You recognize the spectrum homology. And the stable category would be this part down here. It's a single point. So more generally, you can take CP, characteristic P, but then you have to use permutation. C2 is a bit special, everybody's permutation, but in general. So that's recent work we did with Martin Galloway. Much more generally, we studied this category for general group G. And that's also a setting where this type of problem appear. We have closed pieces that we control to some factors. In that case, they would be power quotients that are existent permutation modules. And have I done something wrong? The Zoom is still on. Okay. And what was I saying? It's not.
We cannot see.
It can't be here because.
Okay.
Thank you. And what about this one? Well, this one you can actually, and until recently I didn't know anything about valuation rings besides discrete valuation ring. I'm embarrassed to admit, but you can do this example. So you take not discrete, but a valuation ring with valuation. So you take any abelian group, totally ordered abelian group, and you can create out of that. You can create a ring which has that as valuation ring by taking power series. Essentially, you have to be careful with the coefficients that you can arrange that. The point is that if you can produce such a ring, which is a domain, so it has 0 as a prime ideal, it has a maximal ideal, and it has a prime P which sits in between, which happens to be the intersection of all the powers of M. So M is finitely generated. In that case, it's generated by a single element. You can arrange that. Actually, in that case, you have to. And in fact, the P will be the kernel of the. So this is the kernel of the map from R to its completion at N. And if you play the little game in that case for this Y and the complement, you will see that the spectrum, well, you can see that in that case, the completion at M is a TVR. So the spectrum, the Zariski spectrum of this element is just 2 points. And if you try to trace the map I just described, the map from this to, I'm hiding under the rug that all those things can be done with triangulated categories. But if you have a commutative ring, you look at this derived category, the triangular spectrum, the spectrum in the sense of TT geometry will be the Zariski spectrum of the ring in question. So the last question case is what I was telling you about before. The map here to spec R will pick the top 2 points. It will miss. So as soon as you can miss, as soon as it is possible to miss, it will miss. You have examples, very clear. So our Y friend is this one, and I told you over Y it has to be a bijection. So that's the one. And then where does this go? Well, it goes to the P. 0 here goes to the kernel of this map, which is P. It doesn't go to 0. And so you see that already in that case, as soon as you have 3 points, it is not going to be surjective in general, even in commutative algebra, at least if you're outside of the Theorem setting. Now, of course, depends on your taste. If Theorem is a big loss for you. And I do not know enough other examples at the moment to give you cases outside of commutative algebra where this would not be surjective, but there's no reason that it would be surjective in other settings and just not in commutative algebra. As soon as it fails in one area, it will fail in all. Okay, so I hope it gives you a feeling of what is happening. There is, in general, no hope of knowing just by looking at the 2 pieces how they glue. We need an additional information. That additional information is obtained through completion or through the Tate ring, if you just care about the part of the completion that lives on the open. And you can use that to predict the specialization and actually to recover the whole spectrum from the 2 pieces by analyzing how the attachment happens with this extra. And I think I will just stop my talk here. Thank you. Happy birthday.
Are there any questions?
Have several different lights. Can you see from one how the viewing from the other works? Like if you take a picture like this with many lights, can you use one in order to get information about the data and completion from the other?
Yes, I mean, as I said, it's coming. You want to compute this thing by piece, which is applied inductive reasoning on that. So you'd go with one piece and then study the other one by looking at the trace of the otherwise on each of the two spaces, and then you have one less. It's the usual argument, right? So I think after that is an induction, and then keep track of stuff.
I just have a question about an example, which is if you take a one variable polynomial like kx and look at the origin, then I think the part on the closed set on the origin will be injected out of the ground field. And how is that visualizable over the power series thing? Like you said that that's a visualizable object in some category.
Right. So the one hat will become the unit in the completion. The one hat is the dual of this. I could give you a couple of examples of actual completion of the EY and the FY if you want. I mean, maybe one thing I should have done, if you have 1 minute of patience, is do this one example. I mean, if you take G a P group, and you take the derived category of KG, K is the field of characteristic P, and I am okay. Here I'm lying a little bit because this is not a good category because it's compact and its rigid are different. But I'm just playing with the part where it is. So I'm just so the spectrum of that is of this category. So let's take DP. Right. So that would be the rigid in that example. So let me take the whole category and call that T. So the dualizable objects, that's the spectrum of homology. That's Benson, Carlson, Rickert. And in here you have a maximal ideal, which is just the close point, right? Which is the H plus, the positive part of the homology. And if you do this construction of the Tate ring in that case, so let me take Y to be that thing, and you do the Ty in that case, you will get the double resolution of K. You will get I don't know where you want to put it. With this guy here in degree 0. So you'll get the gadget whose homology will give you the Tate homology of your. And in fact, if you just care about this little triangle, EY, 1, FY, in that case, you will get, well, that will just be K in degree 0. The EY, the FY has to disappear away from the close point. The close point is just caught by forgetting the action going to the derived category, but it's just the acyclic. So here I need to give you an acyclic. Here you take just the projective resolution. Take the projective resolution of K, and here you take the augmented projective, just the cone of this map, okay, the augmented projective resolution. So it has, this one has a K, an extra K to it. And so it is reasonably computable, even if you don't know the big category, you don't know its spectrum, you know, these things you can do before even having Benson, Carlson, Rickert. That's actually another question, how, you know, how useful it is in revisiting old examples to see if the, and so, right. The correct category would be the homotopy category of injectives to do this game correctly. In an actual, what I call the big category, that is one where the rigid and compact coincide, would be the homotopy category of injectives. It is a bit bizarre because it is complete itself. The one hat would be the unit there. It's the injective resolution begin. Yes, so here, for instance, if you complete Y, if you do the EY1, which is the one hat, you will just get the dual of this thing, which gives you an injective solution of the unit. So you can think of the, it's reasonable to think of the homotopy category of injective as actually the completion of that category, except to start with the category which is not an admissible one, which is a compact addition. So at least to justify the name Tate.
Are there any more questions? Okay, so if not, let's do Paul.